Hi there, welcome to another review session for the final exam in Calculus 3208, brought to you by CVLI. Today we're looking at, in this session, higher order derivatives. So what comes after the first derivative? We've already seen some detail about that stuff and we should know a fair bit about it, but we just want to sort of talk about some of the nuts and bolts involved in the algebra and getting from an original function f to its second derivative and beyond. Okay, so let's take a look at some of the details here. We want to talk about higher derivatives of a function and just remind ourselves about what all that means. And we want to talk about understanding higher derivatives as rates of change. That's important. And then we're going to look at the computation of some higher derivatives. So let's take a look. Reminding ourselves here that when we compute higher order derivatives, what we're actually doing is we're taking a function like y equals f of x, and we're going to differentiate it to get its first derivative, f prime, or dy over dx, we sometimes call that. And then we can sort of turn that into an iterative process where we just sort of repeat the same idea, the same thing. We differentiate again to get the second derivative, and again to get the third. And there's, depending on the type of function, there's really no limit to how many times we can differentiate here. We can get all the way to what we might call the nth derivative. And so what is all that? Why would we bother to have higher derivatives? Like, we know that dy over dx, or f prime, represents the slope of the graph, or if we think about it as a function of a relationship between two real variables, then what we have is a rate of change of one with respect to the other. But sometimes it's important for us to remember that, and this is just an example of that in context here, that even multiple derivatives can have meaning. So for instance, if our original function is y equals f of x, the first derivative of that is dy over dx equals f prime, and as we say, the second derivative is d squared y over dx squared, or f double prime of x. So, borrowing an example from physics here, often we refer to a position function, or position s is the variable we usually use in calculus to refer to position. S is a function of time, so we could say s is f of t, some function of time. If I take the derivative of your position, then what I get is how fast is your position changing with respect to time, so ds over dt, or f prime of t, and we usually refer to that as speed, okay? Unless we're going to be fancy and call it velocity if we're getting into vector quantities here. And then we're going to look at the second derivative of that. So the second derivative of this should actually not just be called second derivative here, this should actually be called acceleration. So acceleration is, and this is a good example to use to get this in context. How does the second derivative have meaning? Well, it's the rate of change of the first derivative. So we said that speed was how fast your position is changing with respect to time, and we usually think of acceleration as how fast is your speed changing with respect to time. So are you increasing your speed, speeding up, or are you decreasing your speed, slowing down? Well, that will depend on the sign of the second derivative, whether your acceleration is positive or negative, etc. And we can actually take this further. There is, in terms of position, speed, and acceleration, there is a third derivative that is sometimes used, and the third derivative of position with respect to time, which is actually just the derivative of acceleration, depends on which side of the Atlantic Ocean you live on. If you live in North America, they sometimes call that the jerk, but if you live in the UK, they call that the jolt. So it just depends on which way you look at it. So it's a rate of change of acceleration. So how fast is something accelerating, and how fast is this acceleration changing? So all these things are very layered, and there's not really any limit to how deep we can get with it. But it's important for us to realize that all these things we do with graphs and derivatives and stuff sometimes do actually have some real world meaning, depending on how you apply them. So let's take a look at a quick example. Just a nice simple polynomial here. Find the second derivative. So very easily, f prime of x will be 6x minus 7, and we should be okay with that. And then f double prime, or the second derivative, I just apply a derivative again, and I get 6. It doesn't say to, but if I wanted to find the third derivative here, f triple prime of x, I'm going to get 0, and then all further derivatives after that will be 0 as well, because I'm still just taking the derivative of a constant. Okay, so that's pretty straightforward how we get those. And in this case, we have to find the second derivative of this function. Aha, not so straightforward anymore, because what we have here in the grandest picture is a product rule, whereas each of the components also have these funny exponents, which turn them into chain rules individually. So let's find this derivative and then the second derivative. Okay, so dy over dx is going to be, the derivative of the first one will be 7 outside of 2x plus 3 to the power of 6, multiplied by the derivative of what's inside there, which is 2, multiplied by the second one, which is 3x minus 7 to the power of 5. Okay, so there's my first term in my product rule, plus the derivative of the second business is 5 outside of 3x minus 7 to the power of 4 times the derivative of the guts there, which will be a 3, and then I have to multiply that by the first function, which was the 2x plus 3, all to the power of 7. So before I go and try to differentiate this mess, I can at least simplify a little bit here, because I know that this 7 and this 2 can be combined, as can this 5 and this 3. I'm not going to go expanding anything with powers of 5 or 6, though. So this will be dy over dx simplified a little bit, is 14 times 2x plus 3 to the power of 6 times 3x minus 7 to the power of 5 plus 15 multiplied by 3x minus 7 to the power of 4 times 2x plus 3 to the power of 7. Wow. So that's a lot of stuff, and we're only on the first derivative. So I'm just going to give ourselves a little bit more room here. Take this and slide it up there out of the way a bit. So we're going to have to take that first derivative that we found now and differentiate it. Wow. Okay, so we've got right here a product rule with a chain rule inside each part of the product, and the same story over here. And these constant multiples I'm not going to worry about. I'm going to keep them around but not do much with them, because we know the derivative of a constant multiple of a function is a constant multiple of the derivative of the function. So we're going to call this d squared y over dx squared now, and we're off to the races. So take the 14 and then put all the derivative inside of it. So the derivative of 2x plus 3 to the power of 6 is 6 times 2x plus 3 to the power of 5, multiplied by the derivative of what's inside, which is 2, and then multiplied by 3x minus 7, all to the power of 5. And then I've got to add to that the derivative of the second part, which will be 5 by 3x minus 7 to the power of 4 times its derivative of the guts, which is 3, multiplied by the first bit, which was 2x plus 3, all to the power of 6. So what I've done so far is I've differentiated my first term. Okay, now the second term. So I've got to add to this now 15 times its own pile of business. So the derivative of the first part there is going to be 4 times 3x minus 7 cubed. Okay, so it doesn't look much like a 3, but now it does. So that one's cubed, and then I multiply by the derivative of the inner bits there, which is a 3. And then I'm going to have to add 7 outside of 2x plus 3 to the power of 6, multiplied by the derivative of the inner stuff. So that's just a 2, and then all that gets multiplied by the first function we had in this massive chain here. So that leaves us with 3x minus 7 to the power of 4, and we're somewhere with that now. Okay, so that's a lot of stuff. And the only thing I could see that would be a reasonable simplification for this is sort of combining whatever constants we have there that we can. So let's say that all this will be equal to 14 times 6 is, let's see, 60 and 24. So that's 84 times 2, which is 168, by 2x plus 3 to the power of 5 times 3x minus 7 to the power of 5, plus we've got 5 times 14, which is 70, times 3, which is 210, putting all those constants together, 3x minus 7 to the power of 4 by 2x plus 3 to the power of 6. And then for the second row of stuff that we've got there, all added to what we started with, 15 times 4 is 60. And 60 times 3 is 180, so we have 180 times 3x minus 7 cubed, plus 15 times 7 is 105 times 2, so 210 times 2x plus 3 to the power of 6 times 3x minus 7 to the power of 4. Okay, and that's about as simple as I'm going to want to make that. I may want to make my 8 actually look like an 8, but other than that, I'm not going to do much more with that, because It's about as far as we can go in a reasonable stretch of time. So let's take a look at this third example now. And again, it's another derivative, but it's a straightforward chain rule that we have to deal with here. So let's rewrite f of x as 3x plus 7 all to the power of 1/3. So the first derivative, f prime of x, will be 1/3 of this stuff to the power of negative 1/3 multiplied by the 3 we have inside. And 3 times a third is 1, so we don't need that anymore. And our exponent tells us that this has to be 1 over the cube root of 3x plus 7 if we were simplifying. But we're going to actually look more carefully to find the second derivative at this stuff because it's written as a power rule, which makes it a little bit easier to deal with. Okay, so let's go with the power rule to differentiate that. So f double prime now of x is going to be negative 1/3 times 3x plus 7 to the power of minus 4/3. And then all that has to get multiplied by 3. And then the minus 1/3 and 3 will cancel to leave us just with a negative. So what we end up with in the end here is a negative 1 in the numerator over the cube root of 3x plus 7 to the power of 4. So that was fun. All right, so there's a nice second derivative for us. Let's jump along. And here's the or turn question. So compute the second derivative for that function. So it looks like you've got a quotient rule inside a chain rule, similar to something that we've done earlier, but not quite the same, just to mix it up a little bit. So if you want to take a few minutes and work that out, and I'll jump to the solution slide. So there's the solution. First derivative worked out and second derivative worked out. Simplified, of course, in all the gory detail. So have a minute to look through and check to see if what you did looks like that. And we'll highlight some of the key things we saw here today. We find higher order derivatives by repeating the differentiation process multiple times. Sometimes we call that an iterative process. It says each successive derivative represents the rate of change of the previous function. So we saw a little bit of an example with that. And we can find multiple derivatives in various ways by applying the rules of differentiation and by simplifying to create easier functions to differentiate. So the big thing with finding the second derivative is it's important to simplify the first derivative. Otherwise, you're going to have a messier thing to differentiate the second time around. All right, so I hope that was helpful. Good luck to you. All the best on your exams, and study hard.